Dear colleagues, first of all, I would like to thank the organizers for this very beautiful conference and for the possibility to tell you about our recent results. First principles modeling in our work is first principles molecular dynamics. That's why I would like, first of all, to remind you that this year molecular dynamics turns 70. This term was coined by Bernie Alder and Tom Wainwright in their seminal work. And this work was first reported in Brussels in 1956 and was titled Molecular Dynamics by Electronic Computers. The basic idea is was very simple. We can solve equations of motion for a many atomic system, many body system, and from this redundant information, we can get statistics for this system and kinetics as well. And since we are solving a very fundamental equations for the many body system, classical many body system, we can hope that this method can even predict some phenomena that we could not expect a priori. So this is the major strength of this approach, and I would like to use this talk to make a short advertisement of the second All-Russian conference on molecular dynamics that will take place at the end of June near St. Petersburg in Tsarskoye Selo. And please have a look at the website. There is some interesting historical information about the contribution of Soviet physicists to the beginning of molecular dynamics. About 20 years after the work of Bernie Alder and Tom Wainwright, another seminal paper appeared. This was the paper of Karen and Parinello. They devised some clever approximation to the solution of the electronic structure problem that made this electronic structure calculation at each MD step an order of magnitude faster with those computers that they had at that time. And after this paper, people could allow not to use empirical interatomic potentials. So this is, as we say, quantum molecular dynamics or ab initio or first principles molecular dynamics. In different communities, people can discuss subtle differences in these terms, but they are more or less equal. I will use maybe quantum MD or first principles MD in my talk. What about excitons? I can say that maybe there are two major communities that speak about excitons, that study excitons. The chemical community work with molecules, with isolated objects, and the solid state community that works with periodic systems. And in those two communities, people illustrate optical properties a bit differently, but of course we speak about the same physics, but in slightly different or maybe very different system. But the physics is the same, so our methods, they were devised for chemical systems, but computationally they fit for periodic calculations. So we are, I can say, in both worlds simultaneously. The outline of my talk is as follows. I will speak about two dense fluids, dense fluid hydrogen and dense fluid nitrogen. We have a solid state school here, but I have some excuse. I can refer to the talk of Vadim Brashkin on the first day. He talked about fluids, so I can devote a part of my talk to fluids as well. And then I will describe how we applied the same computational methods for, so to say, solid state system for MOES 2 model layer. So what we are looking for in fluids. So this is usual pressure temperature phase diagram, the melting line, the liquid gas critical point. Here we have molecular fluids, somewhere at high temperatures and high pressures we should have plasma, and there is some kind of transition from fluid to plasma. And nowadays people discuss different variants about the theory of this transition. Either it is a liquid-liquid phase transition, or insulated to metal, or plasma phase transition, or maybe a crossover without any abrupt phenomenon. So our major point is that we think that the equilibrium thermodynamic picture is not good in order to describe very fast experiments that people use to study this phase diagram. And our non-equilibrium excitonic picture fits better for this purpose. So this is these phase diagrams for hydrogen and for nitrogen from the papers of the same group of Alexander Goncharov and co-authors. You see that for hydrogen, the number of points are larger, for nitrogen a bit smaller, but there are many similarities on these phase diagrams. If we look at the hydrogen case, the number of experiments is large, and in addition to diamond anvil cells, people used shock compression to study this this phase diagram. And you see high rating papers. This process has a history about 30 years at this point of time, and the scatter of points are very strong. As you can see on this plot, people usually measure some abrupt process, some feature, either on absorption or reflectance, on, for example, temperature plateau, and they say that this feature is the signature of a phase transition, and put a point on this plot. And then we see this huge scatter and don't know what to think about it. So what about computational approaches? Different types of such approaches have been used, of course, but they are mainly equilibrium and adiabatic, so they do not consider coupling explicitly between ionic subsystem and electronic subsystem. Our methods that we used, they include this coupling explicitly. We made our preliminary calculations with wave packet models for electrons, but the main results were obtained using DFT in the restricted open shell ConSham method. So this animation was obtained with wave packets model, and it illustrate the process. So you see the H2 fluid, you see the big balls, they show protons, you see how these molecules vibrate, and you see these big green molecules, the small balls. In the middle of these molecules are the centers of the electronic wave packets. If the molecule is in its ground state, they coincide. And this big green molecule show the vibronic transfer of energy from oscillations to electronic excitation. So in this model, we see this process qualitatively. And then we will use DFT to consider the first lowest excited state in more details. So this ROX method use quite a simple ansatz. We can express the wave function composed from Kohn-Sham orbitals in the form of two as a sum of two determinants. And in this model, we can solve this electronic structure model quite efficiently and fast for molecular dynamics. And we obtain two higher singly occupied SOMO orbitals. The highest one represents an electron, and the lowest and the lower one represents the hole. So in our first work, we have tried ROX-MD with surface hopping between the ground state and the excited state, just to illustrate that the lifetimes of the system in thermal equilibrium could be up to hundreds of femtoseconds. So it is much longer than the time step in molecular dynamics. That's why we should resolve explicitly these hopping events. We cannot average them in molecular dynamics. And another main point is that in order to analyze how this solution evolves, we should use some localization method for SOMO orbitals, and for this purpose we use Vanier centers. That makes much more sense, gives much more clear visual information than the shape of Kohn-Sham orbitals. On this animation on the left side, you see a kind of small part of the MD trajectory for dense fluid hydrogen. These gray sticks, they are simple H2 molecules. The small green balls are Vanier centers of doubly occupied bonding orbitals. And we have two big balls. These are the Vanier centers of the electron and the hole. And we see how this exciton moves on top of the molecular structure. And two or maybe three, sometimes blue balls are the protons that do not have the bonding orbital in the vicinity. So they are nearly free, so to say. And maybe one of the most important features of our study is shown on the right side. This is the radial distribution function for electron-hole pair. And we see clear Coulomb correlation for this pair at lower temperatures. So these are ionic temperatures, and this is the Coulomb correlation between Vanier centers of two singly occupied orbitals in our model. And we see that at lower temperatures, this Coulomb correlation vanishes. And that's why we can say that at higher temperatures, exciton dissociates. It exists at lower temperatures, and as a coupled Frankel exciton, very small one, and then it dissociates. I will not explain different subtleties. On the basis of such a model, we can devise a mechanism of the transition for hydrogen. So first we have fluid at higher temperatures. Excitons form and disappear to thermal fluctuations. At some threshold temperature, they begin to dissociate faster than they disappear, and this gives us some small plasma-like clusters in this fluid. And when these clusters form in different parts of the fluid in an independent fashion, the fluid begins to absorb light, and only after these clusters merge, the fluid begins to reflect light. And this picture gives a physical explanation to different observed phenomena connected with hydrogen, and the pressures and temperatures for this threshold mechanism, they agree quite nicely with the results of the diamond anvil cells measurements. That is very pleasant for us. What about another fluid? What about nitrogen? It is a more complicated fluid, much more electrons, much more time-consuming calculations. I would like to draw your attention at the amplitude of fluctuations of the instantaneous gap in this system at the temperature of 3000 K, the dense fluid hydrogen. The gap fluctuates from here to here, so several eV. So we can speak about gap, but it is not solid-state physics. In solid-state physics, gap is something very exact and stable. Here it fluctuates. So we should compare the lowest boundary of these oscillations with KT. And from this comparison, we can understand when, due to thermal fluctuations, exciton can form in this fluid. And if we will consider some isochore, for example, 2.5 gram per cubic centimeter, we see that molecular fluid exists up to very high temperature. Excitons, they can form, but they do not dissociate in nitrogen. But the gap becomes very small, and in this point, spontaneous formation of excitons begins. Well, people know that at high pressure and temperatures, fluid nitrogen goes to the polymeric phase, and our model shows the mechanism of this polymerization. Each exciton helps to rearrange the network of covalent bonds, and we can think about it this way. This is a simple sketch of the ground state and the first excited state of the molecular fluid. Some excitons forms when kinetic energy of atoms goes into electronic excitation. Then it evolves for several femtoseconds, maybe hundreds of femtosecond. The positions of atoms rearrange, the covalent bonds rearrange, and then it recombines. But our fluid is in another polymerized state. And there is some difference in internal energy after this one exciton, made something with our system. And this is this energy that is detected in the experiments as the observed latent heat of such a phase transition, so to say. So in case of fluid nitrogen, the same computational methods gives another mechanism. So it is not exciton dissociation, but the polymerization due to the closure of the band gap. And we were very happy that our points, they are shown here as this blue circles. They correspond very nicely with the green symbols that are experimental points of the Goncharov group. No other work could before us explain these points of Goncharov. And so how many time do I have? 8 minutes, thank you. Yes, and now let's go to the MOES2 monolayer. First of all, I would like to illustrate a kind of state-of-art level in this field. In 2024, this paper appeared in PRL. In this paper, using first principles MD, the exciton transfer across the interface of photoactive material and silicon was considered. They considered in the model how the singlet exciton underwent singlet fission and generate two triplet excitons, and the level of DFT theory was a bit less, fundamental than our ROX method, I could say. And these are the snapshots from their molecular dynamics at the time scale of 300-400 femtoseconds. So this is a kind of state-of-art level in this field at this point of time. And this is the MOES2 monolayer that is well known for everybody in this audience, of course. What we have calculated long before, people measured how the peak energy of exciton, how it depends on the temperature. Our calculations are for much higher temperatures, for 500 K, 1000 K, misprint here, and 2000 K. And our peak energies follows the same trend as in this experiment. So we observe nice correspondence of our, quite simple DFT model and experimental data. And if we would like to analyze how this exciton evolves, we should look at the SOMO orbitals. At this picture, you see these orbitals as the density plots, and you see the individual centers of these orbitals. We see that usually each of these orbitals are connected with the d electrons of a particular molybdenum atom. And this is dynamics, how atoms move and how this exciton evolves. On the picture of Vanier centers, it looks a bit differently, but this is just the same data. And we can again calculate the radial distribution function for the exciton. We see very evident Coulomb correlation, and in fact, it does not depend on the temperature very much. And from the same data for different temperatures, we can calculate the diffusion coefficient of the exciton. You see how R squared depends on time, and we see the expected Arrhenius time dependence on the inverse temperature. From these calculations, we can get activation energy for this process. These are evidently the hopping diffusion regime that Vladimir Mansevich introduced in its lecture today. And we see very nice correspondence with experimental data available. We found only four papers with this data, and two of them gave lower values, and two of them gave much higher values. Our results agree quite well with the lower values available. So I would like to conclude with the following statements. First principles, molecular dynamics is able to describe the coupled dynamics of ions and electrons. However, a complete description is far from being possible. But if we find the way to capture the important physics, it is possible to do it. At quite simple DFT level, this approach allowed us to obtain very nice correspondence with experimental data for dense fluids, hydrogen and nitrogen, and our first results for molybdenum S2 monolayer is also encouraging. Thank you. I will be glad to answer the questions if any.
Thank you. So very interesting talk, and the talk is open for discussion. Questions, please. Okay.
Yeah, Volodya, thanks a lot. I'm afraid I have more questions than in the beginning. So the first question, so this is DFT, and you analyze at each MT step, you analyze the wave function you've got. But then, and you analyze the lowest excited state. While DFT is very good, so what is good in DFT is total energy, of course. Maybe in some sense, the wave functions are not that bad as well. I mean, the occupied ones. The excited ones are even worse, right? And what about the Coulomb interaction? So this is your method is certainly one electron, and so I believe, do you miss this Coulomb interaction between attraction? I mean, between hole and an electron, and what is the radius of your exciton? This is the final actually question.
So it's not a very complicated DFT, but it's not the basic DFT. So since we have these two singly occupied orbitals, each of them are singly occupied. I'm very sorry. So they are optimized with electron density in them. So their shape means something for the energy. That's one point. And the second point, since we see this Coulomb correlation, so we capture it.
But I'm afraid not on many particle level. I mean, the correlation in sense of DFT, yes, of course, but this is something else.
Well, as people,
There's something else beyond. I mean,
as people in DFT community believe, the exchange correlation functional somehow captures some many-body effects. So we are believers of this faith.
So okay, Sergey, maybe it's some kind of discussion. We have some more questions.
Thank you for the nice talk. I'm afraid to ask a stupid question. Somehow at very high temperature, you end up with some kind of plasma. I mean, so you have a quite a large twist. You end up with long-range Coulomb interaction. I have no idea how to treat long-range Coulomb correlations with density functional theory, which is a semi-local theory. Yeah. So is there something lost some corrections or what?
No. So on all this picture, we can make calculations only here, and these are our assumptions. So we know I know no methods to make real calculations there. So it's just a kind of hypothesis.
Short question. In school, we learn the chemistry, those bars between atoms, which show chemical bonds. Are your DOMA and SOMA orbitals just those bars from the school chemistry, or is something different?
So we take all quantum orbitals, we find Vanier centers for them, and these centers happen to be in the middle of all the protons. So we know the locations of the protons and the locations of the Vanier centers of doubly occupied bonding orbitals, and then we just connect them with gray sticks, nothing more. So, but it makes sense.
Let me continue this series of questions about DFT and excitons. Let us put it simple. If you stop all molecular dynamics and calculate just the exciton, you're going to receive some radius of exciton and some energy. Yes. If you compare these quantities to the radius and energy of the exciton calculated by some standard way, some two-body way, what's the relation between that?
Yeah, we've since for more S2, there are plenty of results. We could make such a comparison, and for isolated monolayer in vacuum, we observe nice agreement. I can show you all the numbers. I think I can say about 15%.
Okay, I also have one short question concerning the last part of your talk where you showed diffusion coefficients. Seems they're too small. Because typically, or it means that your sample is quite dirty, because typically diffusion coefficients should be 1, 2, 3 centimeters squared per second.
Our samples
is diffusion coefficient seems to be like a hopping regime, not a diffusion.
Our samples is the clearest possible samples in the universe, because it's the models.
Okay, then diffusion coefficient should be 10 times larger, maybe not 10, 100 times. It should be 2.5 centimeters squared.
We will be very happy to maybe
we can discuss.
Yeah. But our temperatures are about 500 K. Maybe this is the reason we have very,
since it's a little bit large, it should be 2000 K to correspond to the energies of the excitons.
I mean that the lattice oscillations play a very big role at these temperatures.
Okay, so thank you so much. We have to move on.